Good day everyone, I am Aljon I, Initan, your discussant for today. And the topic that is assigned to me is the Fundamental Theorem of Arithmetic. For today's objectives, we have, at the end of the lesson, the student should be able to first, state and prove basic theorems of prime numbers. Second, state and exhibit the role of Fundamental Theorem of Arithmetic. So let's start. Definition 3.1. If an integer p that is greater than 1 is called a prime number or simply prime if its only positive divisors are 1 and p itself. An integer greater than 1 that is not a prime is termed composite. For example, among the first positive 10 integers, the only prime numbers are 2, 3, 5, 7, and 9. But remember, 2 is the only even positive integer. Therefore, our composites are 4, 6, 8, and 10. So note, the integer 1 plays a special role for being neither prime nor composite. So for theorem 3.1, if p is a prime and p divides a and b, then p divides a or p divides b. So our proof is, if p divides a, then we need go no further. So let us assume that p cannot divide a, because the only positive divisors of p are 1 and p itself. This implies that the GCD of p and a is equal to 1. In general, the GCD of p and a is equal to p, or the GCD of p and a is equal to 1, according as p divides a or p cannot divide a. Hence, by citing the Euclid's lemma, if a divides the product of b and c with the GCD of a and b is equal to 1, then a divides c. Therefore, we get p divides b. End of proof. For corollary number 1, if p is a prime and p divides the product of a sub 1 times a sub 2 up to a sub n, then p divides a sub k for some k where k is greater than or equal to 1 but less than or equal to n. So our proof is, we need to proceed by induction on n, the number of factors. When n is equal to 1, the stated conclusion obviously holds. Whereas, when n is equal to 2, the result is the content of theorem 3.1. Suppose, as the induction hypothesis, that n is greater than 2, and that whenever p divides a product of less than n factors, it divides at least one of the factors. Now, p divides the product of a sub 1 times a sub 2 up to a sub n. From the theorem 3.1, either p divides a sub n or p divides the product of a sub 1 times a sub 2 up to a sub n minus 1. If p divides a sub n, then we are true. As regards the case where p divides the product of a sub 1 times a sub 2 up to a sub n minus 1, the induction hypothesis ensures that p divides a sub n for some choice of k, with k is greater than or equal to 1 but less than or equal to n minus 1. In any event, p divides one of the integers a sub 1, a sub 2 up to a sub n. End of proof. Next, for the corollary number 2, if p, q sub 1, q sub 2, up to q sub n are all primes, and p divides the product of q sub 1 times q sub 2 up to q sub n, then p is equal to q sub k for some k where k is greater than or equal to 1 but less than or equal to n. So our proof is, by virtue of corollary number 1, we know that p divides q sub k for some k with k is greater than or equal to 1 but less than or equal to n. Being a prime, q sub k is not divisible by any positive integer other than 1 or q sub k itself. Because p is greater than 1, we are forced to conclude that p is equal to q sub k. End of proof. So let's proceed to the theorem 3.2, the Fundamental Theorem of Arithmetic. Every positive integer n that is greater than 1 can be expressed as a product of primes. This representation is unique, apart from the order in which the factors occurs. So our proof is either n is a prime or it is composite. In the former case, there is nothing more to prove if n is composite. Then, there exists an integer d satisfying d divides n, and d is greater than 1 but less than n. Among all such integers d, choose p sub 1 to be the smallest. This is possible by the well-ordering principle. Then p sub 1 must be a prime number. Otherwise, it would have a divisor q with q is greater than 1 but less than p sub 1. But then, q divides p sub 1 and p sub 1 divides n. Imply that q divides n, which contradicts the choice of p sub 1 as the smallest positive divisor, not equal to 1 of n. We therefore may write n is equal to the product of p sub 1 times n sub 1, where p sub 1 is a prime and n sub 1 is greater than 1 but less than n. If n sub 1 happens to be a prime, then we have our representation. In the contrary, the argument is repeated to produce a second prime number, which is the p sub 2, such that n sub 1 is equal to p sub 2 times n sub 2. That is, n is equal to p sub 1 times p sub 2 times n sub 2, where n sub 2 is greater than 1 but less than n sub 1. If n sub 2 is a prime, then it is not necessary to go further. Otherwise, write n sub 2 is equal to the product of p sub 3 times n sub 3. With p sub 3 is prime, we will going to have n is equal to the product of p sub 1 times p sub 2 times p sub 3 times n sub 3, where n sub 3 is greater than 1 but less than n sub 2. The decreasing sequence n that is greater than n sub 1 and n sub 1 that is greater than n sub 2 and n sub 2 that is greater than up to 1 cannot continue indefinitely, so that after a finite number of steps, n sub k minus 1 is a prime, call it p sub k. This leads to the prime factorization. N is equal to the product of p sub 1 times p sub 2 up to p sub k. To establish the second part of the proof, the uniqueness of the prime factorization, let us suppose that the integer n can be represented as the product of primes in two ways. Says, n is equal to the product of p sub 1 times p sub 2 up to p sub r is equal to q sub 1 times q sub 2 up to q sub s. Then r is less than or equal to s, where the p sub r and q sub s are all primes, written in increasing magnitude, so that p sub 1 is less than or equal to p sub 2, then p sub 2 is less than or equal up to p sub r, and q sub 1 is less than or equal to q sub 2, and q sub 2 is less than or equal up to q sub s. Because p sub 1 divides the product of q sub 1 times q sub 2 up to q sub s, by corollary number 2 of theorem 3.1 tells us that p sub 1 is equal to q sub k for some k. But then, p sub 1 is equal to q sub 1. Similar reasoning gives q sub 1 is greater than or equal to p sub 1. Whence, p sub 1 is equal to q sub 1. We may cancel this common factor and obtain the product of p sub 2 times p sub 3 up to p sub r is equal to q sub 2 times q sub 3 up to q sub s. Now, repeat the process to get the p sub 2 is equal to q sub 2. And in turn, p sub 3 times p sub 4 up to p sub r is equal to q sub 3 times q sub 4 up to q sub s. Continue in this fashion if the inequality R is less than S were to hold, we would eventually arrive at 1 is equal to Q sub S plus 1 times Q sub S plus 2 up to Q sub S, which is absorbed because each Q sub S is greater than 1. Hence, R is equal to S. And P sub 1 is equal to Q sub 1. P sub 2 is equal to Q sub 2 up to P sub R is equal to Q sub S. Making the two factorizations of N identical, the proof is now complete. End of proof. So let's proceed to the corollary number 1. Any positive integer n that is greater than 1 can be written uniquely in a canonical form, which is n is equal to p sub 1 raised to k sub 1 times p sub 2 raised to k sub 2 up to p sub I raised to k sub I, where each k sub I is an element of natural number and each p sub I is a prime, with p sub 1 is less than p sub 2 and p sub 2 is less than up to p sub I. So let's have an example. Write n is equal to 2,520 and n is equal to 99,225 in their respective canonical form. Or simply, we're just going to get the prime factorization of each number. For number 1, we have 2,520. The factors are 2 times 2 times 2 times 3 times 3 times 5 times 7. Or simply, 2 raised to 3 times 3 raised to 2 times 5 times 7. For the number 2, we have 99,225. The factors are 3 times 3 times 3 times 3 times 5 times 5 times 7 times 7. Or simply, 3 raised to 4 times 5 raised to 2 times 7 raised to 2. So next, the theorem 3.3. The number square root of p is irrational, where p is prime by Pythagoras. So our proof is, suppose square root of p is a rational number. Say square root of p is equal to a over b, where the GCD of a and b is equal to 1. Squaring both sides of square root of p is equal to a over b, we get p is equal to a squared over b squared, or simply a squared is equal to the product of p times b squared, so that b divides a squared. If b is greater than 1, then by Fundamental Theorem of Arithmetic, there exists a prime p such that p divides b. It follows that p divides a squared. And by Theorem 3.1, p divides a. Hence, p is less than or equal to the GCD of a and b but greater than 1. Which is a contradiction to the assumption that the GCD of a and b is equal to 1, unless b is equal to 1. But if b is equal to 1, then a squared is equal to p, which is impossible. Our supposition that square root of p is a rational number is untenable, and so square root of p must be irrational. End of proof. And for our last theorem, theorem 3.4, there are infinitely many primes by Euclid. Our proof is, let p sub 1 is equal to 2, p sub 2 is equal to 3, p sub 3 is equal to 5, p sub 4 is equal to 7, with the primes in ascending order. And suppose that there is a last prime, say p sub n. Now consider the positive integer m is equal to the product of p sub 1 times p sub 2 times p sub 3 up to p sub n plus 1. Since m is greater than 1 by the Fundamental Theorem of Arithmetic, m is divisible by some prime p sub k. But p sub 1, p sub 2, p sub 3, p sub n are the only prime numbers, so that p sub k must be equal to the 1 of p sub 1, p sub 2, p sub 3 up to p sub n. Then, P sub k divides the product of P sub 1, P sub 2, P sub 3 up to P sub n, and P sub k divides m. Thus, P sub k divides the quantity of n minus the product of P sub 1, P sub 2, P sub 3 up to P sub n. Or equivalently, P sub k divides 1. If and only if P sub k is equal to positive and negative 1, which is a contradiction since P sub k is a prime and P sub k is greater than 1. So, there are infinitely many primes. End of proof. So, that's all for today. Thank you everyone and God bless.